Okay, let's start back up again. So we have this risk neutral set of probabilities, and it has, these probabilities are called, they have different names as so many other things in this course. So risk neutral probabilities. So risk neutral probabilities, these are also called pricing. Let's call it a pricing measure. It's denoted by P tilde. It's also called the equivalent martingale measure. And it's this P tilde, this is P tilde and Q tilde. So these risk neutral probabilities, they have different names. They always mean the same. So, and there are properties under this. So so one property, so one important property, and this is something you will be playing with in your next homework. So one important property is the following, namely that if I remember we had these discounted prices, right? So we have the discounted ones are the ones when you get a tilde on top. So S tilde 1, this was defined to be S1 divided by the money market account's value time 1. Okay, so this was S1 divided by 1 plus R. One important property of these probabilities we have created up here is related to this martingale property that the word martingale is here. So let me try to see if I can show you that. So we also have, of course, the initial stock price in the discounted market. This is just the original one, because we are always pretending like that the initial money market bank account starts out at 1. So I get this idea that I want to compute the expectations under these P tilde and Q tilde probabilities of S1 tilde. Let's try to work out what that is. Okay, so what is that? This is to use the formula. So 1 over R is a constant. It goes outside the expectation. And then what do I have? I have P tilde. I have P tilde times P tilde times well, S1 of P tilde. This is when you go up to upstairs, so that's U. U is the same thing as heads, so I should put a head here, plus, and then I'll have Q tilde, that's the probability of tails, so this is S1 of tails. But I know what S1 in the heads is, and I know what S1 in the tails will be. This is equal to S0 times U, and this one here is equal to S0 times D. Okay, so now I can work out what this here is. I can write this here as 1 over 1 plus R, and then I'll plug in what P tilde is. So we need to remember that formula for P tilde that we had derived somewhere. We have them here on this slide. We had computed what the value at time 0 was for the AD up and what the value was for the AD down. P tilde was 1 plus R minus D divided by U minus D, and the other one, U minus 1 minus R divided by U minus D. So I'm going to take these two expressions and I'll plug them in. I'm going to plug them in for these two values here. So P tilde was 1 plus R minus D divided by U minus D. Everything times is 0U. And likewise over here, I would have U minus 1 minus R divided by U minus D times S0D. Okay, so now it's a question of working out what this expression is. So I have 1 over 1 plus R, I get 1 over U minus D, I get S0. All that stuff can go outside. So I took this part outside, I took this part outside, and then I have my U here. So I'll get U plus UR minus UD plus, what did I do over here? I took the 1 minus U, he went outside, S0 also went outside. And so then I'm left with D times U minus D minus RD. And we see cancellation. We also see that the first part here is, I can put a U outside. This is U 1 plus R. And I can do the same thing over here. I can put a minus a D times 1 plus R. And then I'm in good shape because I have exactly 1 plus R here and I have 1 plus R here. So they will cancel. I also have U minus D downstairs and I have U minus D upstairs. I'm left with S0. Right, so under P tilde, we will have that the expectation of S tilde 1, this is exactly S0. And perhaps a little bit silly, but if I were to compute just the expected return, so this is S0 times 1 plus R, discounted, because this is, the tilde up here signifies discounting, right? This here would also be S0. Right? There's no randomness here. This is not random. But what you see is that the return, the expected return on both the stock discounted and the return on the money market account discounted is constant. So from this, you see that the return, this is an expectation. You see that the return, the expected return on both the stock and the bank is 1 plus R. So this is why you have the word risk neutral. This is where this word risk neutral is coming from. So under this set of probabilities, you expect the stock to grow from where it is to where it is times 1 plus R. And exactly the same thing is what you expect for the bank, right? But in the bank, there's no randomness. So you know that the bank is going to grow from where it is to where it was times 1 plus R. But under this particular set of probabilities that we got ourselves created, we have the same expected return on both the bank and the stock. So that's a feature of this set of risk neutral probabilities. It makes everything grow at the risk neutral rate. Sorry, at the risk-free rate. Everything grows at the rate 1 plus r. Are there any questions on this so far? Okay, so what's going to come next is change of pace. The next, what we want to do, the next goal is, so our next goal is, to create multiple multi-period binomial models. So how would it look like? Well, it would be like if we had our example. So we have an example where we go for, say, 4, and then you can go up to 8, and you could go down to 2. That was the example we had. But then we'll move on. This was at time 1, and then we also need to go up to time 2. So if you continue the tree, then at time 2, no, at time 1, if you're down here, you can then go up, say to 4, and you can go back again to, say, 1. And from 8, you can go up to 16, and you can go down to 4. This property here, so when going up and down equals going down and up, right? So that's what's happening. We go up and down, or we go down and up. So when these two are the same, we say the tree is, and then the word you're looking for is recombining. It doesn't have to be like that. You can also have that going up and then coming down is different than going down and coming up. It depends on the particular binomial model you're looking at. In our case, we will very often have this recombining property. This is just a note. And then you can move on. There can be more periods out here. Right? So what we'll have is, so the randomness, well, this is now generated by these psi's, but they're now different. You're generated by psi 1, psi 2, and so on. And each one of the psi's looks like before. So the IID, so I'm hoping that you will have seen what IID means. It means that they are independent. The independent. So for example, if I looked at the probability that psi 1 would be U, and say psi 3 would be D, and this is the same. So for example, independence would allow you to compute the probability that the first one is U and the third one is D, and would be allowed to compute this simply by taking products. So that's one independence on value, these joint probabilities. So this comma here, this is really an intersection. So you can also write an intersection here if you like that. Right, so right, this is the intersection. So that the probability of psi1 being u and psi3 being d, you can compute that probability simply by taking products. The probability that psi1 is u, so this is what it means to be independent. So you also have identically distributed. That means that the distribution of all these individual random variables is the same. This is the same for all n. And this is a number. This is a number between 0 and 1. So we made it more general. We now have a whole bunch of these random variables, whereas in the one-period model, we only had one. So you can see from this, again, it's specified here, everything is specified under this measure P. But we're not specifying what this particular probability is. We're just saying that this is something that has to be between 0 and 1. We're not saying what it should be. So far, so good. So just a preview. So in the next class, in 622, you will work with a very similar setup. But instead of the size, you're going to be working with something that one could denote by delta B1, delta B2, and so on. The also IID, right? So the independent. But the distributional properties down here are slightly different. The probability that delta, say Bn, is less than x. This is the Gaussian. So this is how would you compute that? This would be something like 1 over root 2 pi. It would be an integral from minus infinity to x of e to the, if the standard Gaussian, then it will be something like this. Right, so the standard normal. So delta Bn is standard normal, mean 0, variance 1. So what we're doing here is in this class, we're not going to be our binomial model is not going to be based on these delta B's. We're going to be working with these psi's. There will be some homeworks from time to time where we will be using these Gaussian distributions. We will also be working with like a sequence of these. So it's always a little bit tricky when we get to this point here, because what the textbook has decided to do is to develop. So when you're in the thin textbook, this one, he has just developed all the theory for this particular specification where the size, we take the values u and d. And then what happens is that when you get into the next course and you switch over to the thicker one, the second one, you have to redo this theory to cover the case where you're dealing with Gaussian variables instead of these Bernoullis down here. And so what I find that a little bit silly that we have to spend our time and then you have to basically redo the same material half a year from now, or in the beginning of the spring semester in the next course. And so the way that I'm going to teach this is set you up such that you can it suffices for you just to have the next few weeks of class, and then when you get into 622, you will already be set up for dealing with the material related to independent Gaussian random variables. So we kind of do two things in the next few weeks that will be useful for you. One of the things will be useful directly in this class, and then the next one is going to be useful for you in your next in the following class. But what that means is that we have to move over and start reading in this thicker textbook. So we need to get our hands on that if you don't have it. And if you go to the schedule, you'll see what sections in there we're going to be reading. So the theory that we're going to develop here, this is going to be sufficiently general, so it can include, of course, what we need, but it'll also include what you're going to need in continuous time. And in continuous time, this B here, that's going to be like a Brownian motion, and a Brownian motion is intimately linked to the Gaussian distribution. So to save some time and effort, we're going to do this in one go in my class. It also means that what is going to come now is, I know this is a challenge. It will be a challenge for some of you. It has been so in the past, so you got to hang in there a little bit. The sections in here that we're going to be looking at, they're not a priori going to have much to do with quantitative finance. And so what we're going to be looking at is these two first sections here. And it's in particular this thing called information and conditioning. This is really like, how does one model the flow of information? This is what this information is about. And there are words in here that you probably haven't seen much of before. There's something called sigma algebras. And then there's something called conditional expectations. Conditional expectations you've probably seen before, but sigma algebras you might never have seen before. So this is what's going to come in today's lecture, and it will come again. We'll finish this up hopefully next week. So take a deep breath. This is going to be, there's going to be an increase here in level of abstraction. Before I get started on that, are there any questions on what we've done so far today? Okay. Then we'll get started on this crash course in measured integration theory. So this here is going to be a mini course in the field of the topic is called measured integration. So this here is going to be today, and this thing here, this is next time. There's something called a triplet. So we need to know. This is today. So what is a measure space? So this is denoted by omega. And then you're going to have this F, and then you're going to have this P. So what is that? Well, there are three components. It's a triplet. So the first component is omega. This is called the sample space. It's called the sample or the probability space. So examples could be, we could have omega be what we've been doing, heads and tails. It could be an interval of the form 0, 1. Often one has it open to the left, close to the right. It could also be R, and it could be something really, really crazy. So this here is this is the one period binomial. This one here, I'm going to write down here. This is going to be what you need in 622. and down. So this is, we're not going to be doing this, but just to give you an idea about how general this space can be. This here can be the set of functions. So these are these functions that are, f goes from say 0 to 1 to r, if is continuous, and if at 0 is 0. So the underlying space, this can be quite complicated, right? So here you have 2 points. This is what we're doing, or what we've been doing last just before the break. You can have an interval point. You can have the real line, and the last one here is this is what you need in 622. You have the space of continuous functions that are 0, 0. This thing down here is what you need to you need to work with in order to understand the Brownian motion setup. So we will not specify. We often do not specify. We often don't specify omega. It's just in the background. Okay, so that was the first entry. It says it's a set of points. It's just for us, it's a set of points. And these points, they could be functions, they could be vectors, they could be points in R, or they could be H and T. One of the two. Set of points. That was the first entry. Then the second one, F here. This is the more complicated one. This is a sigma algebra. Okay, so that is probably a new word. So this is a system. This is a collection of subsets of omega such that, and well, 3 conditions must be met. The first one is it's a collection of subsets of omega. Okay, so the first condition is that omega must be inside F. Right, so the elements of F are sets. So it's a collection of subsets of omega, right? So F belongs to capital F is a subset of omega, right? So we write this as F and then like that. Right, so an element in F is a subset of omega. This is what makes it a little bit tricky, right? This is more more abstract, and then what we might be used to. So that's a sigma algebra. A sigma algebra is a collection of sets where each of these sets is a subset of omega, and it must satisfy a bunch of properties. One of them is that omega has to be in there. The second one is if I take a set inside F, then it must be the case that the complement, and the complement is nothing else than what is not inside the set, that should also be inside F. So if I take a set, I look at its complement, the complement must also be in the sigma algebra. The third, and the reason it is called sigma up here, this sigma here, this has to do with this property there. Sigma, this is something about countable. So if I take sets Fn inside F for all natural numbers, take a sequence of sets inside F, then it should also be the case that the union of all these sets is inside F. So just to contrast, F is an algebra. If 1 and 2 and this slightly different version of 3, so 3 prime, if I can take only finitely many, and then I'll have that the union is in there. So the word sigma, it refers to you being able to go from 1 to infinity and take a union and stable inside the sigma algebra. If you can only take finitely many, arbitrary but finitely many, so here n is a natural number. You can take finitely many and then you stay inside there, we just call it algebra. So you get yourself such a collection of sets. If properties 1, 2, and 3 hold, well then you're good. So what could be examples here? One example is I take F to be 2 to the omega. You might have seen that notation. This is nothing else than those are the sets F such that F is a subset of omega. So this is the power set. Or all omega's subsets. So for example, if we are in our setting where we have heads and tails, that was the top one. If I take heads and tails, then I look at instead of all subsets, well, what would it be? This would be I need to form all possible subsets of omega, so I will be able to take heads and tails. I'll be able to take heads, tails, and the empty set. And these are all the possible subsets that I can find of omega. I can find omega itself. I can find the element that just has H, the element that just has T, and then I can find the empty set. So that's the example for the one period binomial model we will have. We will also have, we will need, we will need, in our class, we're going to be needing more than just these ones here. You can start taking, if you do a two period model, then you'll have HT, and maybe you'll have the product. Right, so what's the product space? This will be, I flip 2 points. How do I flip 2 points? I can get H, T, T, H, and TT. And then again, I can look at the, in this case, I can look at the power set 2 to the omega. And it will be a lot to write out now, but how do you form, what kind of subsets can you form of 4-element space? Well, you can form itself, you can form HH, you can form HH union, HT, and so on. I'm not going to write them all out. You'll have a bunch of sets in here. And that will be a sigma algebra. These are not particularly, yeah, there are many others, and when you move into, when you move away from just having a discrete space here, you start having uncountably many elements in your set. Then stuff changes, and for example, if I take omega to be this half open interval, I could take a set A, which is inside this half open interval. Then sigma of A. So again, you see this symbol sigma. You see this word, this letter sigma, which is the one that we've had before. It's the same letter, it's the same Greek letter as the one that's being used up in the word, up in the name if it's a sigma algebra. So that's sigma. You just put that outside here, and what that means is this is the smallest sigma algebra containing A. Okay, so how would that look like? So if I write out what sigma of A is, I'll always have to have omega, so I'll always have to have the set 0 to 1. I'll always have to have the empty set. Then it's going to be the smallest sigma algebra containing A, so I need to have A in here. And the question is, what else should I stick in here? What else should I stick in here? Any guesses? Suggestions? Could I stop my list here where I'll just have omega, the empty set, and A? Would it be okay to stop here? would this here be, I cannot have anything, this is, I cannot take anything away that would not make it a sigma algebra, but the question is this a sigma algebra? Well, for it to be a sigma algebra, we have to have the properties. We have to have the properties 1, 2, and 3. So we have omega. What about unions? If I start taking unions of things in here, I take A union the empty set. Is that in there? Is A union the entire interval in there? Yeah, I mean, A union the empty set is going to be A. The entire set union A, well, that's going to be the entire set because A was inside. What about the complement? What about the complement is number 2, does that hold? If I take anything inside here, these 3 sets, would the complement also be there? But if I take the complement of the whole set, I'm going to get the empty set, so that's good. If I take the complement of the empty set, I'm going to get the whole set, so that works. But the problem is with A, if I take the complement of A, I don't find it. So I need to put in A complement here, and then this is going to give me the smallest sigma algebra. A more famous example is, and this is called the Borel sigma algebra. So here we're thinking about if I take, I can stick to omega being this half open set. Then the Borel algebra, the Borel sigma algebra, this is the so we call it what should we call it, B of 0 to 1. This is the smallest. It's the smallest sigma algebra containing sets of the form A to B1 union A2 to B2 union to, say, AN BN. Where we have 0, A1, B1, A2, B2, up to 1. So that's the Borel sigma algebra. You guarantee that inside the Borel sigma algebra, you can find all these half-open intervals. Okay, so you guys, you got very quiet. Are we hanging in there so far? We're hanging in there so far. Okay. So here are some questions. So some random questions, just maybe to think about. Some questions. So one question is, if f and g sigma algebras. If F and G are sigma algebras, is, say, F intersection with G and F union G also sigma algebras? And this turns out to be tricky. Intersections, yes. Unions, no. And this one here, this intersection property, this is really useful to show that there's always a smallest sigma algebra containing certain sets. For example, certain sets, for example, the half-open intervals. Because the way that you do it is that every time you take intersection, you're going to get something that is smaller. And you can always find a system, you can always find a sigma algebra that contains half-open intervals, say, because you can just look at the sigma algebra that contains all intervals, and all sets. And then you start taking intersections over sigma algebras then that contains these half-open intervals, right? So this is useful for this because you can then write, so if you want to write this B of, if you want to write B of 0 to 1, we write this here as the intersection over F. F is a sigma algebra containing half-open intervals. So that's how you that's a characterization of the Borel sigma algebra. No, this is more frustrating. So you cannot take unions, and so why can you not take unions? So if you look at what we had over here, if I take like two sets here, if I take the union of sigma A union sigma say B, I'll use the formula. I'll get the whole space, the empty set. I'll get A complement, and then I'll get B and B's complement. And that's not a sigma algebra because it's not stable, it's not closed under units. For example, inside here, I don't find A union B. This is not to be found in the list. So when it comes to performing operations on these sigma algebras, be a bit careful because some of the operations are fine, intersections in particular, but unions, no, it doesn't work. So that was just a little bit about sigma algebras, how we do go about constructing it. A natural question that comes up is something with this Borel sigma algebra. Is the Borel sigma algebra, say on this interval, is this the same as the subset of all subsets of this interval? I mean, this one here is clearly bigger. And the answer here is no. That is one argument for why this is one argument for why we would need these sigma algebras. There are sets that cannot. There are sets, subsets of the interval 0 to 1 that are not inside this collection, this intersection up here. And then, so when we get here, then students, you will then typically ask, can you please give me an example? And giving an example is hard. So try to Google, or even better, try to go on YouTube. Try YouTubing a non-Borel set. These things are not something you can visualize. Another way to try to get at, so what's the big deal with this sigma algebra structure, right? So it begs the question, so why not work with 2 to the 0, 1 instead of say these Borel sets? Why do we need to introduce this notion of a sigma algebra? I mean, this here is a main example. Borel sets, this is a main class of sets. Well, these sets that live inside sigma algebras, they are often called for measurable sets. So sets in F. So I'm trying to get at this question here in the last half an hour. So sets in F, they're also called measurable sets. And so the thinking here is that when you have a one-dimensional object, we're thinking about length. When you're thinking about it in 2, and then you're thinking about area. And when we're in 3 dimensions, you're thinking about it in volume. So if this here is in 1D, so now we're thinking about length. If you were to be in D2, we would put a square here. If you were to be in D3, we would put a power 3 up here. So sets here are called measurable sets. So why not work with all of them instead of restricting our attention? Well, the problem is, so the problem is that there are sets in, say, 0, 1. There are sets in here that cannot be given. That cannot be given a meaningful length. Okay, so we're claiming now that there are sets that are so ugly in this interval that I cannot assign a length to it. Keep in mind, if I'm talking about these much nicer sets inside the Borel algebra, it's quite straightforward to assign a length to such sets here, right? They are disjoint. Right? So this set here, how would we assign length to it? Well, it's a disjoint union of half open intervals, right? So each interval is going to have a length, and the length of this interval here will be B2 minus B1, right? So B2 minus B1, this is going to be that piece. This piece here is going to have B1 minus A1, okay? So the disjoint, so I'll put a plus here. So I'll have the length of, so this is unlike, if I were to look at length of this A1, B1, union A2, B2, union AN, what do we call them, capital N? No, N. If I were to assign length to such a set here, it would be a lot easier. This would just be B1 minus A1 plus B2 minus A2 plus all the way down to Bn minus A. So the problem is that there are these sets. I'm claiming that there are these sets in the interval 0 to 1 that cannot meaningfully be assigned a number, a length, such that this happens. Okay, how on earth am I going to convince you that this is true? How am I going to convince you that something like this is true? And the way that I'm going to do this is something called Banach-Tarski. So here we have to work in R3. But given that my ability to draw pictures in R3 is extremely limited, my pictures are going to be in R2. So I will draw in R2 because I have tried many times to make pictures in R3 and this simply just doesn't work. I will draw in R2. Okay, so what is Banach-Tarski's paradox? This is again, this is a fantastic thing with today's technology. Try to go on YouTube and grab a video about this paradox. We will not be able to specifically show you all the glorifying details because these sets that we are dealing with that cannot be assigned length, these are not sets that you can draw on a computer screen. It's not something you can draw on a piece of paper. This is something that exists abstractly. So it's something that one works with math-wise, but it doesn't mean that you can't try to get an idea about what the problems are by looking at these videos out on YouTube. And there are really some amazing ones. So here's the gist of the Banach-Tarski's paradox. So if you want to measure, so we're looking at this here as an R3, right? So we want to, in R3, the thing that we want to measure is volume, right? So we want to measure the volume of a can of water. We want to measure the volume of a book, something, a three-dimensional object, right? Height, width, and depth. So what do we do here? So our measure of volume must be, well, what should it satisfy? We should be able to move it. So it should be translation invariant. Right, so we can just move it. The volume doesn't change. It doesn't change by moving the set. Right. If I have a box here of dental floss, I figure out what the volume is of this dental floss. Okay, so I figure out what the volume is here, then I move the set over here. It doesn't change the volume of my box of dental floss. That seems like a reasonable notion that volume should have. I can just move the set, I can move it wherever I want, and it doesn't change the number that I assign as its volume. Okay, that seems reasonable. And the other thing that we want our set to do is I want to be able to rotate it. Rotation invariant. So you can rotate without changing volume. So again, I take my dental floss box. I figured out what the volume is, and then what I do is I move it like that. this should not change. It shouldn't, I can even flip it upside down. This should not change whatever value or number I have assigned as the dental floss box volume. I should be able to, first I should be able to translate it, and then I should be able to rotate it however I want, upside down, turn around, whatever you want to do. This should not change the number that I have assigned as its volume. So if the starting point is that you want to do this, so if you want to be able to measure, so here that means to assign volume. If you want to be able to measure, that is assign volume to all sets in R3. So if you want to be able to measure, that is, grab an arbitrary set in R3 and assign a volume to it, and your notion of volume satisfy these two properties, then you have to live with, then you face the paradox. And this is why it's called the Banach-Saski paradox. And this paradox here, this can be a little bit hard to believe at first. So what you do is you take a ball. So this is where my ability to draw in 3D comes in. So you have to imagine that this here is a three-dimensional picture, but I'm not, when I start drawing in this axis, it always gets messed up. So I'm going to make a ball. So trying to make a ball. And you want to be able to rotate it. You want to be able to rotate the ball. And you want to be able to move it around. Like, so I can rotate it, I can move the ball from up here to down here. I can turn the ball around and I can move it. It doesn't change the volume of it. So the crazy part is, and this is what Banach-Saski says, that you can find two disjoint sets let me call them E and E prime, such that the volume of the ball, I can find two disjoint sets in E prime, so that means that the intersect is empty, such that the volume of ball is equal to the volume of E, which is equal to the volume of E prime. So what this is saying is that if you want to be able to measure, all sets, and you want this measure, in this case is volume, you want it to be such that when I move the object, the set around, I flip it, I rotate it, I translate it, I don't change the set's volume, I have to live with this property that I can take a ball, I can break it up, I can break the ball into pieces, take these pieces apart, I can glue the pieces together as two disjoint sets. And these two disjoint sets each have the same volume as the original ball. if you go on YouTube, the expression that they use here is how to grow. So how to create the sun from a sand corn. So you take a piece of itty bitty little piece of sand, and you can crack this sand into a bunch of disjoint sets, reassemble them, and then each of these two collection of pieces of sand, you will now have the same value, same volume as the original sand corn. So if you can do it once, you do it again, and then you keep doing it, and at some point you've created the sun out of the sand corn. This is clearly something that we can't have. So something has got to give, and the thing, it is hard to give up these two principles, that rotation and translation can somehow mess up the notion of a volume. So the only other thing that has to give to, the only other thing that can give is restrict attention to something where this doesn't happen. And up here, there are simply too many sets, too many crazy sets that will allow something like this to happen. Whereas if you restrict attention to this Borel sigma algebra, which is much smaller, well, it won't happen there. I know this can be a lot to take in. We have never seen measuring integration theory before. This level of momentum, where the starting point is an abstract collection of sets. This F here. Why would we ever need to do that? Well, the reason is that the most benign example, which is the interval from 0 to 1, it's not important here whether this one here is open or closed. This is not a big deal. You can close it, you can keep it open. This is not a big deal. There has to be a convention, and the typical convention that people use is to keep it open on the left and close on the right. So I'm just going to follow the usual thing here. The problem is that if I'm looking at all possible subsets of this interval 0 to 1, there are sets in there that are so crazy that it allows me to take a ball, break it up into these crazy sets, reassemble these crazy sets, and get two new balls that each have the same size as the old one. So there are too many sets in here, so you need to restrict attention to something that is smaller. Okay, so what you do is you restrict attention to this class here of Borel sets, for example. And inside here, all the sets inside here, they can meaningfully be given a notion of volume. And this is what's going to come up next here. But before I start talking about, like, we have three elements here. We have omega f. The last one is the p. This is the volume assigner. That's the measure that we're going to measure the sets with. Before I do that, let me just pause here and see if we have any questions. Normally when we do these lectures on the chalkboard, I look at the students at this point, and most students will have a little bit of a sad look on their face. And but here I can't see you guys, so you need to tell me what part of this I should say more about. Are there any questions or comments? One question that has come up in the past in this lecture here has been, so we have in this example here, what we see is you give me a set A, and I prescribe a formula. I prescribe a formula that looks like this. And so that means that given a set A, there is a specific formula. There's a way to list what sigma of A is. So this is not, that's not the case. That's not the case for the Borel sigma algebra. Here, the thing that we know is it's the smallest sigma algebra containing sets of this form. But it doesn't say, there's no formula for it. It's not like this, here's how you do it. If you want to get all the Borel sets, this is there's a formula for it. And here there are like 4 elements in that sigma algebra. Down here we have a very, very large number of elements inside the Borel sigma algebra. And there are many other things inside the Borel sigma algebra than just these half-open intervals. So maybe we should try to explore that a little bit. So what could one expect to find? So about the Borel sigma algebra. So because this is our main example about this Borel sigma algebra, there's no formula. There's no formula, so all we know is, well, we know that it's a sigma algebra. We know it contains half open. It contains all half open intervals, and then it has the smallest property. It's the smallest. It is the smallest sigma algebra. I should say it's the smallest such sigma algebra. But for example, like there are other things in there. If I know we have the definition of the sigma algebra, so we know it has these 3 properties. 17. So we know it satisfies these 3 properties. So we know that omega's in there, that guy's in there, and then we have it's countable. We can take countable unions, and we'll be in there. But there are other things in there. If I take 2 sets inside a sigma algebra, I can also get at, like, what can I get at? I can get at something like, if I take the complement of A, I know I'm going to be in there. If I take B's complement, I'm going to be in there. And if I take a union, because A's complement and B's complement in there, the union is going to be in there. And then I take the complement again. I know that this is an element. This is going to be an element inside here. And if I work out what this is A intersection with B. So I'm also stable under intersections. If I take 2 sets in there, not only is the union in there, the intersection is also in there. I can do the same thing with the complement. If I take A less than B, this is something I can write as A intersection with B's complement, and this is going to be in there. This belongs in there when A and B are there. So you see, there are more sets than just these half-open intervals. For example, we can do intersections. You can also do, if we are in the Borel sigma algebra case, I can look at something like, if I pick pick x in this interval 0 to 1. Then it's not clear that do we have, because x is not written as a half open interval, so do we have that x by itself is inside this B? This is not clear because what we're allowed to do is we're allowed to have these half open intervals, and x by itself, I cannot write x by itself as a half open interval. But what I can do is I can write x. I can write x as something in terms of half open intervals. So if I do x minus a little bit, minus 1 over n up to x. And then I take the intersection. So what I'm looking at here is an interval. I have my x, and then I'm going down to x minus a little bit. I'm going down to x minus a little bit, and in all of these half open intervals, I'll have x, and when I take the intersection of all of them, I'm going to get exactly x. And this here is a half open interval, so I know that this is an element in B. What we just did was we've argued that B is also, any sigma algebra is also going to be stable under intersections. Okay, so if each element in the intersection is also, when I know that each element in the intersection is measurable, well, then the intersection is going to be the 2. But so this thing here, this is also going to be an element in there. So yes, these single points, they are also Borel sets. So we don't have a formula. We don't know how all these Borel sets they look like. If you want to argue that a certain set is a Borel set, we have to write it somehow in terms of these half open intervals, their intersections, or their unions, or their complements. And so what is going on in the Banach-Saskis paradox is that there are sets in the interval, subsets in the interval 0 to 1 that cannot be written in terms of these basic operations on these half open intervals. Yeah, there's no formula for how one generates all these sets inside B. Are there any questions at this point? So we got a few minutes left, and the last thing I want to tell you guys about is the third component in our triplet. So now hopefully we have some idea about what the first two components are. We have some idea about what omega is, we have some idea about what F is. Omega is a bunch of points. F is a collection of subsets of omega that satisfy a certain structure. Now what's P? So P is the last thing. P is our measure. P is a probability measure. And what does that mean? P is a probability measure. Well, so that means that it's a function. Its domain is F. This here is P's domain. And its codomain is the interval 0 to 1. This is P's codomain. Okay, so it's a function. You're allowed to put sets in the sigma algebra into F. And what does it do? It satisfies, it's a probability measure. It's a probability measure if two things hold. First one is if I take the entire set, which I know belongs to F, if I take the entire set, plug it in to P, I'm going to get 1, which is inside P's codomain. And the second part is if I take sets. So if I take sets for Fn in F, the disjoint, so take a bunch of disjoint sets. And then I want to compute the probability of this union. This is the second property of what it means to be a probability measure. I take the probability of the union. This can be computed by computing the individual probabilities and adding them up. So P is a probability measure. What you're allowed to measure are sets inside F. That's why F is said to contain all the measurable sets. And it has the structure that if I take the entire space, the sample space omega, plug it into P, I'm going to get 1. And if I take disjoint sets and I try to measure these disjoint sets, then the probability of the measure of their union, this is just going to be adding up the individual components. So that's the formal definition of what it means to be a probability measure. And so, as an example, we can look at the Lebesgue measure. And let's write it down in the first case. If I look at the Lebesgue measure of, say, an interval A to B, it would, so for 0, A, the Lebesgue measure is going to be B minus A. More generally, if I want to do the Lebesgue measure for A1 to B1 union AN BN, we'll get exactly that formula we had before. This would be A1 minus B1 plus all the way down to AN. No, it should be another way around. It should be B1 minus A1, BN minus AN. So we have gotten ourselves the Lebesgue measure defined on all these half-open intervals. But how do we define? But how to define the Lebesgue measure on the Borel sets? So not just the sets generating the Borel sigma algebra. Right, here we got ourselves defined the Lebesgue measure on all these half-open intervals, and you can see when A is 0 and B is 1, this is exactly equal to 1, right? So it fits up neatly up into this formula. But how do we measure not just these half-open intervals? Because as we just saw, there are a lot more general sets inside this sigma algebra, not just these half-open intervals. So this is going to be, we'll talk about this next time. This is called Cacciadori. Better spell this correctly. This is Cacciadori extension theorem. So the word you wanna, if you wanna prep a little bit, try to look up Carl-Theodoris theorem. Okay, I think this is plenty for today. I know this mesh integration theory. This is it's a step up in terms of abstraction, maybe compared to at least compared to what we've been doing in the first parts of the class. We are gonna the reason we're going through. Walk back to myself. The reason that we're going back to the reason we're going through this more abstract mesh integration theory is, as I said, twofold. So there's madness. There's a reason behind the madness, and the madness is that why do something that is so complicated when we don't really need it in this class? Well, it's because come spring you are going to be needing this. There is no way you can do continuous time finance and Brownian motion without this sort of without these sorts of tools. So we're biting the bullet and doing it now, thereby giving you more time in the spring to do other things. So that's why we're taking this part of the second textbook and going through it now. And that being said, it really will allow us to properly go through the multi-period binomial model. So for example, there was one of the questions in the very beginning of the class that said, what's the difference between this course and the undergraduate course that currently seems to be overlapping? Well, one difference is going to be that in our course, in our 421 course, we will have time to do American options, which is one of the later chapters in the thin book. And there, if you want to understand American options and these closed form expressions that you can get for some of these American options, you really need this theory. It is just not the case. It is not the case that the sigma algebras that we're working with will be those, the set of all subsets. The set of all subsets is simply just way too big. If you want to study the underlying model in some of these models that are being used for American derivatives. So there's just no way around it. We need this. You have to restrict attention to a strictly smaller subset than all possible subsets. And that subset, that will be the measurable sets that we can assign a measure to. So volume and so there's no way around it. If you want to do this, say American options. And we do, of course, we want to try some American options in this course. Okay, enough talk for me. We have a few minutes left. Are there any questions or comments? Okay, if not, I just want to remind you that we have office hours on Thursday morning, and we have office hours on Friday morning with me, and then tomorrow morning there are problem session with the TA, and there's a set of problems posted that he's going to work on tomorrow morning, and I'll upload these videos and notes at some point today. There was a question. What time are the office hours on Thursday? The office hours on Thursday is 10:30 until 11:30, and the office hours on Friday are from 10 to 11. You can find that. You can find these links and passcodes. You can find this. I think the one on Friday morning, you have to have a passcode, and the passcode is somewhere to be found in one of the announcements on Canvas. Okay, are there any other questions before we say see you later? Okay, then I wish you well. I will see you guys later.